GPUIterator, bridging the gap between Chapel and GPU platforms.
Thanks, Michelle, for introduction. So hi, everybody. Hi, everyone. So my name is Akihiro. I'm a research scientist at Rice University. And as I mentioned earlier, today I'm going to talk about how do we support GPU in Chapel. And let me first give you the background. And what you see here is the number of GPU in the top 500 list. And as you can see here, number of GPU are rapidly increasing. Actually, in the early days, like 2005 to 2010, it was actually like a clear speed accelerator and IBM cell-based accelerator. But 2010 was when the NVIDIA GPU came in. And after that, so number of GPU are rapidly increasing. And now, actually, there are around 138 GPU are in the 500 list. And actually, the number include their other accelerator like Xeon Phi or PZ or something like that. But as you can imagine, most of them are NVIDIA or AMD GPU. And when it comes to GPU programming in Chapel, and actually you could utilize the Chapel's most resolution concept, which is my favorite, and we could actually start with a really high-level specification like a forall loop. So as you can see, we have a forall loop here, and at the very beginning, maybe you could just write a forall loop and run it on the CPU for the proof of concept purpose. And if performance is sufficient, it's okay, you can just keep the original code. But if you need more performance, maybe you could consider utilizing the, say, automatic parallelism compiler for generating the GPU code from the Chapel forall, and I'm aware of a few approaches from the other group. So I know the Illinois team invented something like automatic Chapel domain compiler to the GPU, and also I'm aware that AMD folks was working on that. And it's actually okay, but sometimes it doesn't give a really nice performance for some cases. So if you really need a more performance, maybe we could consider writing the GPU kernel using the CUDA OpenCL. It doesn't have to be GPU, the CUDA or OpenCL. Maybe you could utilize AMD's like a heaps or something like that. And basically, you can write C++ or C-based accelerator program, and you can invoke it from Chapel. And this is our focus on paper. So this paper, so suppose we have to use some other external language, and but how do we write the GPU code and how do we use it from Chapel, and so that we can keep the great portability in Chapel. So that's our focus of paper. And let me give you more details. So this is, suppose we are writing some forall code, and this is a really simple program where we are just doing the vector copy. We have the two array here, and then just assign statement in the forall loop, and suppose we want to run it on GPU. And Chapel really has a really nice feature, C interoperability feature, where you can write a separate C file on your right. And you can also declare the specification of the function in the Chapel code, and you can just invoke it from the Chapel side. So say we have a GPU VC function here, and you can declare the external function declaration here, and you can invoke it from the Chapel side, and which is actually great. But so one problem is that this code is not super portable because so you have to switch back and forth between the original version and GPU version because GPU is not always faster than CPU. So if you are running this loop with really tiny loops, like say anyways like 32 or 64, maybe CPU is faster than GPU. But in that case, so if you want to change, okay, I'm not going to use this version, we have to go back to the original version, we have to somehow comment out this version and comment in this version or something like that. This is not very portable code. So the question is that how do we easily switch back and forth these two versions? And also, in some cases, like some AMD GPU, which is a gift within the CPU, which doesn't have a super large data transfer cost, so which sometimes give a really nice performance when we are doing the hybrid execution, like a CPU 50%, GPU 50%, something like that. Actually, I'm gonna give you more detail later. But sometimes hybrid execution is really give some nice performance, and also when we want to run this code on the distributed machine. So say, Vlad talk about the distributed domain, but it's actually non-trivial for us to implement this GPU version with the domain mapped, chapter domain, distributed domain. So our question is that, so what is an appropriate and portable interface? And that brings this two version, like so as I mentioned earlier. So actually we don't want to comment in, comment out these codes so that we can switch back and forth these one. And so yeah, what was a really nice programming interface between two versions. So yeah, our solution is that they're kind of in between version. Say, actually we can just keep the original version, like you can still write the for loop, but the only difference is that you can write some special iterator, what we call GPUIterator, which can be invoked within the for loop. And say we can just wrap the original iteration space in the GPUIterator, and we have to give some additional argument, which is function pointer to the actual GPU function, and also the CPU percent. And this is for the hybrid execution, what I mentioned before. But basically, so this code is kind of very portable because we can keep the original version, and we can also specify the pointer to the GPU function as well. So it really allows us to switch back and forth between different versions. So that's our contribution. We designed and implemented GPUIterator, and we also, I'm going to show you some performance numbers and with different CPU execution policy later. And before we dive into more details, so let me first talk about the GPUIterator. Actually, Brad did a really nice introduction of the GPUIterator, and actually I can skip this, but basically, so we can generate any sequence, and we can also schedule each iteration into the several processor element. In this case, what a coincidence. I was going to talk about the Fibonacci iterator, and in this case, we just schedule the first half of Fibonacci numbers into the CPU1, and the other part will be going to the CPU2. So which is really nice. So similarly, even for a GPU iterator, we did a very similar thing. Like actually, we just override the default behavior of the GPU iterator, and actually on your left is the really rough behavior of the original GPU for where suppose we have n to 1 to n range, and it actually internally divides this whole iteration space into the several CPU chunks. And again, this is done internally in GPU module. And similarly, so what we have done with GPUIterator is that so for given range, like say 1 to n, we internally divide the original iteration space into two chunks first. One is for the CPU portion, other is for the GPU portion. And after that, we can also divide further so that we can distribute these tasks into the several CPU and GPU. This is a very basic idea, but it really works well. And let me also give you the more details on the GPUIterator. And as I mentioned earlier, so in the bottom code is very similar to the original for loop, but again, only difference is that so you can invoke the GPUIterator within the for loop, and so you have to give additional argument, but which is actually very tiny. And the first one is that the GPU callback, which is called after our GPUIterator divides the original iteration space. So we recall that our code internally divides the iteration space into the CPU portion, GPU portion. And after that, so our GPUIterator gives some lower bound and then higher bounds of the divided iteration space. So which can be, which can be used from some lambda function here, like after the GPU module divided this iteration space, you can get the lower bound and the higher bound and the number of elements, which is actually number of elements is very redundant, but for the current version, so we just gave this to the user so the user can verify the GPUIterator collectively computed their subdomains. And after, so you get some subspace for the GPU, you can just call the original C function so that we can run the code on GPU. And so please also recall that we can also specify the percentage where you can specify how many percent goes to the CPU portion and how many percent goes to the GPU portion, which is really portable, I think. And also, so our GPUIterator also supports distributed domain. And as you may notice, so in the first line, we have our distributed domain using the DMAP. And one nice thing about Chapter is that you can easily support the distributed domain in the for loop. So you can just, for now, just ignore the GPUIterator. So for in I in D will be will be the distributed distribution across multiple nodes. And we can do the similar thing even with the GPUIterator, where that you can just give the distributed domain into the GPUIterator so that we can run this code on the different nodes. So, but to do so, actually, we need to modify the round function a little bit. But actually, the change is really small. So basically, you can just put some chapel array API, which is a local slice that allows us to get some local portion of the distributed array. And the actual change is very small. You can just, I think we may recall this. So the original version was AB, but now we just keep the local portion of the distributed array. And this actually code change is really small, but you can easily make this code like a more distributed friendly code. And so also, Brad also talked about the zipper for loop. And you can basically iterate over multiple items. And our GPUIterator also support that. And but the one restriction is that so you have to put the GPUIterator in the first argument so that we can make it the reader iterator. Actually, reader iterator is responsible for the creating task. So that's why you have to do so. But I don't think this is a major restriction. And okay, so actually, so this is really technical detail, but so to enable GPUIterator, actually we created some new local model, and which contains two sub-logics. One is CPU local and GPU local, so that the GPUIterator internally aware of these processor elements. And but basically, from the user point of view, you can just specify some environmental variable, which is a chapel local model GPU, and that's it. So you don't need to do anything else. And for actual module of the GPUIterator is available on my GitHub. And if I have time, I'm gonna give you more a little bit. But for now, I just say that so our module is open source, and you can easily use it. And this is a little bit detail of the implementation of the GPUIterator, and actual implementation is more than this. But I just wanted to showcase the really basic concept of the GPUIterator implementation. And so internally, so we create two tasks. One is for the CPU portion, and the other is for GPU portion using the for loop. And so actually, this code is not great, but for line number 2, and if the sub-local is 0, which is for the CPU portion, we just compute the sub-range for CPU portion, and by getting some local information. So you can get a number of tasks from the local information and on line number 3, and after that we can create the tasks for each CPU portion. And for GPU portion is so far actually we only support one GPU, but we can actually easily extend it to the more multiple GPU version. But basically, so for the sub-local one is GPU, and we just invoke the callback function that are given from the users. That's this is implementation of GPUIterator. And then so actually this is more for the user who wants to use the GPUIterator, and he also need to write the GPU code as well. And basically, so because we are using the chapel C interoperability features, and at first, so chapel area resides on the host DRAM, and but to use GPU, you need allocate the data on GPU using the maybe CUDA function or OpenCL function, something like that. And after that, you have to do the host to device transfer. And after that, you need to run the kernel on GPU. And after that, you invoke the device to host transfer so that we can get a result from the native side. And yeah, this is a requirement for those who use GPUIterator. But I think so yeah. Usually this code is very similar to the typical GPU code, and I don't think that this is a very huge restriction. Okay, so let me talk about the performance implementation. Actually, we did a lot of performance evaluation on a different platform, and they are like an Intel-based CPU plus NVIDIA-based CPU, and also we evaluated our GPU on the IBM system, and yeah, I also did evaluation on my MacBook Pro, which has Intel GPU and AMD GPU as well. And so for Chapel Comparer, we used the nearly latest version of Chapel, which is 1.20. And for GPU comparison, we used NVCC. And for AMD and Intel GPU, we used the OpenCL version, which is NVIDIA 10.0. And yeah, let's talk about the other parameters I use. And one is the tasking, and for CUDA version, so we use the QSLED for tasking layer. But for OpenCL, actually, I got some error saying that if we invoke the OpenCL API from the QSLED task, I got some segmentation fault error, so I had to choose FIFO as a tasking layer. But yeah, so hopefully, I'm going to use the QSLED at some point, but for now, we just use a FIFO for the chapel tasking layer. And what I see here is a list of applications we use for this evaluation, and basically more like numerical computation, and it includes some machine learning application as well. And before we talk about the performance numbers, so let me first talk about how many lines are modified and added. So yeah, in chapel code, actually it's changed as a very minimum, as I mentioned earlier. It's usually like 6 lines, 11. It actually really depends on how many kernels we have. And actually, for logistic regression, and it has 2 kernels, and which means that we need to write two lambda function for that. So which is why the number of modified lines around 11. But yeah, basically, so for one kernel application, it only requires like a 6-line code modification for that. And yeah, also this is not focus of our paper, but just for your information, I just put how many lines are required for implementing the CUDA and OpenCL code, which is around like 50 lines to the sometimes it takes like 500 codes, but yeah, again, this is out of focus for now. Okay, so yeah, let's talk about the performance. And yeah, X-axis shows the application, the Y-axis shows the speed up over the original for loop, and which means the higher is better. And as I mentioned earlier, so GPUIterator allows us to easily explore the different variants. So you can just put the CPU% as a command line argument, so you can change the configuration very easily. So suppose the left-hand side, left one means like a C, 100% means that the whole iteration space goes to the CPU. But if you go right, like 75 and 25 and 50, 50, so we are gradually increasing the percentage for the GPU portion. And so yeah, as you can see, so GPU version shows really good performance number, particularly for the 3 applications, like a graph shows, logistic regression, matrix multiplication, which can give like an order of magnitude speed up. But sometimes, as I mentioned earlier, sometimes the GPU is not, GPU doesn't give a really good performance because the computation is too small, like for vector copy, as you can imagine. So the computation is too small to get a great performance on GPU. So that's why we don't see performance degradation on GPU side. But yeah, our point is that so we have a really nice interface so that we can explore the different configurations. So yeah, if you really don't like the GPU performance, you can easily switch back to the CPU version to get a good performance. And this is also, yeah, it's a performance number on another platform, which is a Xeon plus the NVIDIA GPU, and we see the similar trend where that, yeah, vector copy and stream doesn't give a good performance on GPU, and the other three are good performance. And also, yeah, someone also needs to know how good GPU version compared to the really optimized CPU version, because so for original forward version I showed before is not really optimized. So, but maybe someone really interested in the what if we use a plus library for the chapter part and how many speed up we can get. So yeah, that's the results, and we chose different matrix size, and we compute matrix multiplication on the actually another platform, Core i5 plus Titan XP platform, and yeah. So as we can see, so yeah, actually, so we have several variants. One is a brass version on CPU, and our GPUIterator version has 3 variants. One is a very naive CUDA code, and optimized CUDA code, and the Cooper's version. And yeah, if the matrix size is very small, actually the last version is much better than the GPU version, but as we increase the number of inputs, we can get really nice performance with GPU version. So again, yeah, we can actually explore the different variants using our GPUIterator as well. And so yeah, also, yeah, let me show you the benefit of the hybrid execution. So this is the result on my MacBook Pro, where we have the Intel GPU or AMD GPU, and in that case, and we get the highest performance number with half execution, and this is because yeah, the CPU performance, when the CPU performance and GPU performance is quite similar, and which really, yeah, gives us a really nice performance improvement with 50-50 execution, because so we can just distribute tasks evenly onto the CPU and GPU. And yeah, I just wanted to show the case where the hybrid execution is beneficial. And yeah, so lastly, so I also wanted to show how good our GPU is on the multiple node environment, and we just changed the number of nodes. And yeah, actually this application graph shows the really great scalability even with CPU, but we can get additional speed up using our GPUIterator, because we can accelerate the original forward loop using the CUDA, and yeah, we get like a 14 times performance improvement on the 4 node compared to the 1 node execution on CPU. Okay, so yeah, let me conclude. So yeah, in this talk, we introduced our GPUIterator, which allows us to easily switch back and forth different performance variants, and so that we can get a performance, really great performance. And as I mentioned earlier, source code is available on GitHub. And so yeah, for future, so we actually only support the forward loop so far, and yeah, hopefully, yeah, we can get support reduction as well. And also, yeah, we only evaluate black shows on the multiple node environment. So yeah, hopefully we're going to get another application to evaluate. And yeah, also, so this is more like a very ideal, but it would be great if we can do the automatic selection of the CPU and GPU percentage, so that we can automatically come up with great performance factors, right, or something like that. Yeah, so that's it. So yeah, I'm very happy to take the questions. Thank you.
We have time for some questions.
Yeah. Is it correct that you rely on closures and only rely on closures for the lambda?
Yes. So what do you mean relying on? So
yeah. So you need to define a closure to be able to make use of the GPU operator.
Yes. Right. Yeah.
isn't that dangerous? So I remember a talk from, I think, Eric Meyer, who created the link stuff in C# for Microsoft Research.
Mm-hmm.
And I remember a talk that the semantics in C# for closures is really well, is hairy. Let's call it like that. But and now you even have a closure with parallelism and an external interface. So I think that's pretty dangerous. Or
I think I see your point. Yeah, actually, so this closure will not going to be run in parallel. This is just I mean so how to say. So I think your concern is that what if we run it this portion in parallel, right?
yes, well, yeah, sure, yeah.
Yeah. So
It's an iterator. So it closes over A and B here.
mm-hmm.
But suppose,
A and B are passed in by reference, though, right, by pointer.
yeah.
Yeah.
So I don't.
Yeah, it's not being executed out of the context of the forall, so I think it's fine. I mean, it's got the same scope of execution as the forall.
Yeah, well, seems dangerous to me. But maybe I'm
Yeah, so actually, I think your concern is important, but for now, our assumption is that user already writes a parallel code, right? And so original version, we have a forward loop, and we have some assignment here. In this case, A sub I equal B sub I, and I think with that, I think user already know it's very safe to run it on parallel. And of course, it may have some delays, but yeah, for this particular case, I think we are safe to assume that we can run it on parallel.
Yeah, the lab doesn't necessarily mean it's a complicated closure, because that anonymous function is line 1 out in the global scope, or is that inside something else?
Yeah.
Is it global, or?
Oh yeah, yes, yeah. It actually can take global because A and B are global, and
So I think a lot of the closure complexity comes in from the allocation of things that are allocated locally within the closure. And if you're just handing it fixed size pointers to things that are in the global space anyway.
yeah, well,
Yeah. no,
So maybe
it's-
something
it's a
we should
question
take
of
offline.
interesting.
Because I was
Yeah,
actually gonna say, I think we should push, because right now you have two different function bodies. They're
right,
doing the same thing.
exactly right.
Right,
Yeah,
which
yeah.
really what you want is the same loop body, with the same loop body
Mhm.
to be executed on the GPU as it's executed in it. And so you've got that inconsistency. So I wanted to push more into the lambda and make it.
Interesting.
All right, but we're gonna switch to the next talk. Could somebody get that door? Because they've got it, thank you, appreciate it. So, thank you.
Thank you.